So remember when we talked about Newton's laws of motion, and we said that his first law of motion said that an object in motion, such as these beautiful little leaves falling to earth, will continue in that motion unless acted upon by some outside force. And that's the same thing for the wind, because we talked about these pressure gradient forces from high, that's my PGF, pressure gradient force, to a low pressure. Okay, and then that's going to move air that way. Okay, unless some force acts upon it. Well, the two forces that actually can act upon air that's moving we call wind. The forces that can redirect wind are friction, and the second one is the Coriolis force. Now friction, I'm not going to go much more into. Friction actually, as you might imagine, works against the direction of motion. It's kind of that rubbing sort of thing. So if our pressure gradient force is this way, so that the initial wind seems like it should go this way, then we have the force of friction this way. Okay, so that's my PGF. Now, a cool thing, and I think I talked about this in physics, didn't I? Where actually we can add those to what we call vectors, and looks like the resulting vector would be in the same direction, but just a little bit shorter. Okay, so that would be maybe be the net force. Okay, so that's friction. The other force is actually called the Coriolis force, and it's an apparent redirection of wind due to the Earth spinning on its axis of rotation. Okay, so I'll kind of spend a little bit of time talking about the Coriolis force, although not as much time as I spend in my 16-week meteorology class. You're just going to have to take that 16-week intro meteorology class. So the Coriolis force, abbreviated CF, is caused by the Earth spinning on its axis. I'm going to kind of talk you through it, but one of the things that I want you to know is that in the northern hemisphere, it deflects things to the right. It deflects air that's moving to the right. So in other words, if my air, here's my high and here's my low, okay, oops, how do I do that? Yeah. And if the air would go this way, okay, that's the way it should go, it's going to deflect it to the right. Now, I'm bad about my left and rights, but do you see where a deflection to the right is like that due to the Coriolis force? Okay, that's what that means, okay? So this deflection is, like I said, an apparent deflection, which kind of says, well, it's not real. Well, it just appears that way, sort of, because the Earth is spinning. So here we've got, I've got, like the caption says, a projectile, and it could be a jet, whoops, it could be a jet that actually has left the Earth's surface. You see we're at 90 degrees latitude, and we're going to fly towards the equator. Okay, so it's left the Earth's surface. Now, the Earth actually is spinning. The Earth is rotating. So I compare these two, and I see that the Earth, how do I want to say this? The Earth underneath the jet has moved straight, okay, but the Earth underneath the jet has rotated, so now it's actually going to end up at B when it started to look like it was going to end up at A. Is that okay? So it's it looks like it's following a line of longitude, but the silly Earth rotated. Earth's not silly, but it rotated counterclockwise, just like you're seeing here. Okay, so that actually caused it to appear to land at a different, or go to a different location. So this right here is what, this last one is what it appears it was deflected to the right in the northern hemisphere. Does that look like a right deflection to me? It does to me. Okay. So that's kind of what we have going. That's the Coriolis force. And it only works on large bodies of water or air. Okay. And the Coriolis force, there's many kind of features of it, but an important feature of it is this apparent deflection or apparent spin only works most near the poles, strongest near the poles, and it peters out to zero at the equator, which has consequences for our hurricanes and such.